Hello, everyone. In this lecture, we will talk about identifying zeros and multiplicities of zeros of a polynomial function. And later on, we will talk about two different types of divisions. And of course, we have other important theorems and formulas as well. So let's start with identifying zeros. And well, we've seen this before, what zeros are of a polynomial are. So basically, zeros of a polynomial are the values that make the function or the polynomial zero. For example, if we have f of x equals to 0, then the x which make this function or this polynomial 0 are called the zeros of the function. Basically, here we have f of x equals to 0. And if, let's say, for example, if our f of x is, let's take simple example, +1, a linear polynomial, polynomial of degree 1, then we have to find the root of this one, or the zeros or real roots of this polynomial. What we do is we just set this function equals to 0, okay? And this is how we find the polynomial. Now we can solve this, because this is just a linear equation now. And the solution to this equation are what we call the zeros of the function, or another name is the real roots of the polynomial or the function, or the equation, actually, not the function, okay? And every root or every zero of a polynomial function has a multiplicity. Now, what is multiplicity? Multiplicity is the degree associated with the factor of that zero. For example, let's just take this example. First, let's try to find the zeros of this function. So we have m of x equals to x to the 5th minus 10x to the 4th plus 25x cubed. Now, to solve or to find the zeros of this, we set it to 0 to find. We set this function to 0, and then we have this on the right side. And then, as you can see, we have x to the 5th, x to the 4th, and x cubed. So we can factor out x cubed, and then we have x squared plus minus 10x plus 25 left. And then this one, we can factor it out. We can factorize it. We have this. And of course, this is a perfect square. So this is x minus 5 squared. And we have x cubed on the other side. Okay. So if we are asked to solve this, then we have x equals to 0 or x equals to 5. These are the two values that make this whole thing 0. Therefore, these two numbers are zeros of the function or real roots of this equation, okay? This equation. So the next is, what is the multiplicity of these two roots or these two zeros? Now, if we look at this, for the first term, this 0 comes from this, and this 5 comes from this one, because these are factors of the polynomial. One is x to the cube, and the other one is x minus 5 to the squared. So this x factor is raised to the power of 3, and this x minus 5 is raised to the power of 2. So the multiplicity of this one is, multiplicity is 3, which is this power, and multiplicity for this 0 is that power, which is 2. Therefore, we have a multiplicity of 2 right here, and multiplicity of 3 for the second one. Okay. Now, this is how we find the multiplicity as well as the 0 itself. So first, we find the 0. Just, it's kind of solving an equation. And then for each 0, we can find, by looking at the degree, we can find the multiplicity of that 0. And the next is to figure out whether this is an odd or an even number, okay, the multiplicities. So here we have an odd multiplicity, an odd number, and this is an even number. Based on this, if the multiplicity is odd, if it is odd, then that point, this is the point on the graph, the point is a cross point. If the multiplicity is even, then it is a touch point. Okay. Now, what do we mean by this? So basically, what we are saying is when we solve this equation, we found x equals to 0 and x equals to 5, and we call this zeros of the polynomial function, right? But in other words, these two numbers are points where the graph of this function touches the x-axis. Okay, either touches or crosses the x-axis. Okay, so there are two possibilities because these are intercept. Both of them, they are x-intercept. When we talk in terms of this equation or this function, these are both of them, they are x-intercepts. Therefore, there is possibility that the graph touches the x-axis and return back, or the graph touches it, crosses it, and continue. Okay. Now, how do we determine without graphing, without plotting the graph? By just looking at the multiplicity of that factor. So for the first one, this is one intercept at x equals to 0. Now, does it touch it and return back from the direction it comes, or it crosses the line, the x-axis? Since this multiplicity is it's odd, then the graph crosses that the x-axis at that point. But the second one, at x equals to 5, at this point, since the multiplicity is 2, which is even, then the graph touches the x-axis and returns back to the same direction where it came from. Okay, therefore this is what we have right here. So this one, we call it a cross point because the graph crosses the x-axis at that point or through that point. And this one is a touch point. It touch the x-axis and returns. It could be even from below or from above, it doesn't matter, but it doesn't cross the x-axis. Okay, so this is some of the information that we can get from multiplicities of zeros of a function. And another important theorem here is the intermediate value theorem. And this one basically says if we have two values of x, let's call them x and a and b, and if a is less than b, and when we evaluate the function at a, which is if we find f of a and if we find f of b, and if these two values have opposite sign, one is, let's say, negative and the other one is positive, then the graph of f, or if the function f has at least 1 0 between the numbers a and b, or in the interval a comma b. Okay, on this interval it has at least 1 0, which means it touches or crosses the x-axis at least once. Okay, so let's look at this one. Let's take a here, some number, and b is here. So since both of them are positive, then definitely a is less than b. And then if we evaluate f at x equals to a, then the f of a is here and f of b is here. And as you can see, this is positive and this is negative number. So they have opposite sign. So that means the graph crosses the x-axis, at least crosses or touches. Most probably it crosses because it's opposite. So the graph or the function has at least 0, and that 0 is at this point. Okay. And another example is we have here, which has just between a and b, it has 3 different zeros. Here it has 1 0, but here it has 3 different zeros. Now, how about the other way? If we have, let's say a is less than b, but f of a and f of b have the same sign. If, let's say, both of them are positive, this is f of a and f of b. So this one, it's, if this is the case, if we don't have this, then this is inconclusive. Sometimes they may have 0, sometimes they may not. Okay, and a simple example of this is we have it here. So a is less than b. We pick a to be less than b, and then f of a and f of b are both of them right here, which means both of them are positive. And if you see between a and b, the graph doesn't touch the x-axis, and that means the function doesn't have a 0 between a and b. Okay, so this the theorem doesn't work for if f of a and f of b are both positive. And another possibility or another thing is we have a and b, and we f of a and f of b are both positive. And as you can see, between a and b, the graph touches the x-axis twice, so it has 2 zeros. Okay, so we have 2 different conclusions here. Therefore, for this case, if both f of a and f of b have the same sign, then we cannot say, or we cannot conclude. Okay, so it's inconclusive. Sometimes it may have a 0, sometimes it may not. It depends. So we cannot use this theorem if they have the same sign. Okay, now let's use this example and find if the function f has a 0 between -4 and -3. So here we will use the intermediate value theorem. Yes. Okay, so to do this, we have these 2 values, and of course this is our a and this is our b, and obviously a is less than b because they are negative numbers. And now let's find f of a, which is f of -4. So we have to evaluate this, and f of -4, that's a big number. 16 times 16. What is this number? 256, I guess. Yeah, so this is 256 plus 6 times, this is, since it's negative, this is -64. Minus 26 times -4 plus 15. And oops, 256, this is 256. So 256 minus, this is 4 to 8, and this is plus 4 to 104 plus 50. And if we add this, minus 384 so I got negative 9. And for f of negative 3, it will be negative 3 to the 4th. That will be 81 minus 6 times negative 27 minus 26 times negative 23 plus 15. So we have 81 plus this is 162, I guess. And well, this is plus, so this has to be minus. And we have here 878 plus 15. Therefore, this will be it will be 12. Okay. So based on this, the intermediate value theorem, what do we know? F of A and F of B have opposite signs. F of minus 4 and F of minus 3 have opposite signs. Therefore, the function f has at least 1, 0 on the interval between -4 and -3. Okay, so this is the importance of the intermediate value theorem. It tells us just by evaluating the function on those two endpoints, we can determine whether it has at least a 0, 1, 0 or not. Okay, and the next is the number of turning points. So based on the degree of the polynomial, we can figure out how many turning points it may have. So the possible turning points for a polynomial function with degree n is n minus 1 at most. Okay, for example, if we have x squared, how many turning points do we expect this one to have? Our n is 2, therefore 2 minus 1, we expect at least the function to have at least one turning point, and that's the case. So the graph for x squared, we know this one. This is what it looks like, and there is only one turning point. It doesn't have more than that. Okay, and for x cubed, we would expect 3 minus 1, which is 2 turning points. Okay, and similarly, if the polynomial, the degree goes up, then we can by using this definition, we can figure out how many turning points we can expect from the graph of the function. So the turning points are points like this one. Okay, it was increasing, for example, here, and then at this point it starts to decrease. It's decreasing at this point, it's a turning point, then it starts to increase. So the points where it changes from increasing to decreasing or from decreasing to increasing, those are what we call the turning points. All right, so so far we have seen information, or we have seen different properties or behaviors of graph of a function. So by using all this, now we can sketch the graph of a polynomial function. Now, here are the steps that we need to use to sketch the graph of a polynomial function. So here we have, I put the steps, and on the right side, we have we have an example. So the first one is we need to determine the end behaviors. We learned this one in our last lecture. And the end behaviors, to understand the end behavior of a graph, we just look at the first term. So always look at the first term or the leading term. In this case, for this example, our leading term is minus x to the power of 4. That's what we call the leading term. Now, if the coefficient of that leading term is negative, the graph opens downward, okay? And the two endpoints, we look at the this exponent or the power of that leading term, and if this is even, then the two endpoints, they go together to the same direction. In this case, since this is negative and this is even, then the endpoints, they go down to the same direction. Left down, down left, and down right. If this was positive, then we would expect them to go this direction. Okay, left up or up, left up or up left, and up right. Okay, so here we have the end behavior just by using this leading term. The next is determine the y-intercept or find the y-intercept. And to find the y-intercept, just evaluate the function at x equals to 0. Basically, which means find f of 0. So in this case, since our function is t, then t of 0, we substitute 0 in each of these x values. So this will be 0, so it's just -8. Therefore, the point is 0, -28. So it's somewhere in here. Just to make it short, I didn't go too far. So if, let's say this is -28, then that means the graph touched the y-axis at this point. This is the y-intercept. And again, we find the zeros of the function. Again, the zeros of a function has more or less the same interpretation with the with x-intercept. Okay, so find the zeros of a function and then its multiplicity. So to find the zeros of a function, just set this one to 0. Set this function equals to 0. Okay, so minus x to the 4th plus 11x squared minus 28 equals to 0. And how do we factorize this one? Probably you have seen this one somewhere, like on your homeworks at the beginning of this course or in other classes of algebra. But to do this, to factorize this one, you can, because this is just, you can consider this one as quadratic. So let u equals to x squared. I will replace this with x squared by u. And if this is u, then this will be u squared, because x to the 4th is x squared squared. Okay, this is what it means. Therefore, I can write this one as minus u squared plus 11u minus 28 equals to 0. And to factorize this one, we have u squared minus 11u plus 24. Okay, and well, we can multiply this by negative, so this is useless. This negative, we don't care about it. And now we can factorize this one, and the numbers for this one, for their sum to be -11 and their product to be 24 are 4. Wait, this is 8. Sorry, this is 28. They are 4 and 11 and 7. Okay, so -4 and -7. So we have u minus 4 and u minus 7 equals to 0. Now I go back and replace u by this guy. And then we have this step. Okay, if you replace this one, we have x squared minus 4 and x squared minus 7 equals to 0. And then each of this can be factorized further. So this is x minus 2 and x plus 2. Okay, because this is product of the product of x minus 2 and x plus 2. And this one similarly is the product of x minus root 7 and product of and x plus root 7. Therefore, we have how many? We have 4 different factors. And the zeros are plus or minus 2. We have negative, we have positive 2, we have negative 2, we have positive square root 7, negative square root of 7. All these numbers, 4 of them, they make the function 0. So they are zeros of the function. Therefore, I have plus or minus 2 plus or minus root 7. I will remove this one because we have it already there. Okay. Okay. So now by looking at this, what's the multiplicity? Well, for each of them, the multiplicity is 1 because there is no power here. The power is 1 for each of them. Therefore, the multiplicity for all of them is 1. And if you see, if you remember, if the multiplicity is an odd number, then the graph crosses the x-axis. It's a crossing point, not touch point. It's a cross point. Okay. Therefore, at each of these points, the graph crosses the x-axis. Okay. So those points are this. These are the 4 points, and we know it crosses those points, and we know the y intercept is somewhere in here. So we know it goes from this one, it goes up because it has to touch this x-axis, at this point. Okay, so definitely it has to go up in order to touch it here. Okay, that's one idea now. So from here we go up, it touches the x-axis here. We go, it goes somewhere up. It goes up. We don't know how high it goes, but we know it goes up because it has to return back and touch the x-axis at this point. So it has to go up and come back, and then again it touches the x-axis here. And similarly, on the left side we have the same situation. Okay, and then the endpoints are what we predicted earlier. So this is our sketch, just based on this information. Okay, and of course, if you have symmetry, or if you really remember, or if you really understand the symmetry, you can use that symmetry because you can determine it based on this one. If this is true, then it's an even function. If this is true, then it's an odd function. And another point is, for smoothness or for accuracy of this graph, you can add more points. Let's say, for example, between this point and this point, you can add more points. So maybe does it go this way or this way? We don't know. So you can add more points so that this will be more accurate. And of course, on this side, and on this side, of course, and of course on this side. Okay. By adding more points, you can make it more smooth and more accurate. So this is just a sketch of the graph. Now, going back, if we go to this one now, we create the traditional way. We use the traditional way by preparing the table of values. For arbitrary values of x, we find the values of y, and then we plot them. And this is the graph. As you can see, it's more or less, it looks like our sketch, even though it's not that smooth or that accurate, our sketches. So this is the actual graph, and our sketch, it has this similar directions. It follows similar shape, but of course it's not that accurate. So as you can see, this is the correct graph. Okay, now we go to division of polynomials. Now, before we go to division of polynomials, now let's remind ourselves how we can divide two real numbers. Let's say, for example, if I have two big numbers, one big number, let's call it like 1, 2, 5, 4, 6, I don't know, maybe these are enough, divided by 3, for example, just to make it simple. So using by hand, how do we divide this? Well, first we look at the first number. If the first number divides this one, can divide this one, then we divide it. If not, we take the next number. So in this case, 2 is smaller than 3, therefore it cannot divide 3. So we take 25. Now 25 divided by 3 is 8. 8 times 3 is 24. Okay, then we subtract, and the remainder is 1. We bring this one down, 14. 14 divided by 3 is 4. 4 times 3 is 12. And then we have 2. Then we bring this one down, 26. Again, 8. 8 times 24, 8 times 3, sorry, 8 times 3 is 24. Then we subtract. This is 2. And we bring this one down, 27. And this is 9. Oh, we picked perfect number. And this is 27, and the remainder is 0. Okay, so this is how we divide numbers by hand if we don't use technology, right? And the idea for division of polynomials is more or less the same. Okay, now we have two different ways, or we have two different methods. One is called the long division, which is basically this one. And the other one is the synthetic division. The synthetic division is more special one, and we will see it later. But now let's start with the long division. Okay. So the long division is basically you follow these steps, exactly like what we do with real numbers. That's how we divide two polynomial functions. Now, for example, we have this polynomial divided by this one. The first thing that we need to do is we reorder them. We bring the largest power to the front, and then we put them in order. So let's try it that way. X to the fourth minus 3x cubed plus 5x squared minus 7x plus 1 divided by x squared. Now there is one special number here, not special, but don't get confused by this. It's not square, just x, 0x, then plus 3. So probably you are asking, why do we need this 0 number here? The reason is it helps us with dividing or with following the steps. And of course, the value of this number doesn't change. It's 0 still. 0 times x is 0. But what we are trying to do is we are trying to fill the empty space here. We have x squared and we have the constant, but we don't have x. We don't have the first power here. So we are filling that gap, because when we perform the division, then we need that gap to be filled. Okay. So if we don't have that one, either on this side or on this side, it doesn't matter which side. But if, for example, if you don't have this number, then use this empty, or this placeholder, and write 0x cubed. So what we are interested in is just the cube, so that we can follow all the steps in a similar way. Okay. Therefore, always use this placeholder to help you understand or perform the division without any mistakes. So this was 3x squared, x cubed plus. Okay, now let's go and start dividing the polynomials. Okay, so what we have is this divided by this one. Now, always what we do is you take the first term. We don't care about the rest. Look at the first term, and from this one, the first term. This is our first term from this divisor, and from this dividend, the first term is 2x to the 4th. Therefore, 2x to the 4th divided by x squared. If we simplify this, what do we get? This is 2x squared. So this one divided by this one is just simplify now, and which is this number. Therefore, I write that number. This is the quotient when we divide this one by this. And now we multiply this by each of this. So 2x squared times x squared is 4x, 2x to the 4th. 2x squared times 0x is 0x cubed. 2x squared times 3 is 6x squared. Now you subtract this and use this parenthesis because this subtraction is for all these terms. Okay, so use the parenthesis, put all of them in parentheses. Now 2x to the 4th minus 2x to the 4th is 0. Negative 3x cubed minus 0x cubed. This is still 0. So any number minus 0 is that number itself. Therefore, this doesn't change anything. But this is the reason why we needed this. Remember, if there was no this one, if there was no this placeholder, then probably some of us would write this number here. So it would be x cubed minus x squared. If I write this one here, then x cubed minus x squared is not something that we can subtract because they are not the same type. And that's why, that's why we need this placeholder. Okay, therefore this is negative 3x cubed, and 5x squared minus 6x squared is negative x squared. Okay, and then we bring this 2 down here. Now again, take the first term and divide it by x squared. Negative 3x cubed divided by x squared. If you simplify this, you get negative 3x. So I put that negative 3x here, and then again multiply this. Now I don't type this. I just use the second one, negative 3x times x squared. This is negative 3x squared. Negative 3, that one is again 0x squared. Negative 3x times this is negative 9. And again we have negative. So if this is 0, negative x squared is again negative x squared, that number say by itself. And then negative 7x minus 9. Sorry, this is x. Minus 9x. So this becomes plus. Therefore, it's 2x. And then I bring that one down. And again, the first term divided by this one. Negative x squared divided by x squared. This is just negative 1. So I have negative 1 here. Negative 1 times this is negative x squared. Negative 1 times this is 0x. And negative 1 times 3 is negative 3. Therefore, if we subtract again, this is 0, this is 2x, and 1 minus 3 is plus 4. Okay. Now, we found, or we divided the polynomial, the first polynomial, or the larger polynomial by the smaller polynomial, and we have a remainder. So it's always good idea, or it's good to put it in a square box. If you put the remainder on in a box. Now, how can we write this one? This one divided by this is equals to this, and we have remainder. Okay. Therefore, we can say this number is 2x squared minus 3x minus 1. This is the quotient. And this is divisor. And this number by itself, the big number is dividend, and this is remainder. Okay, so these are the four different terms. Now, in the next, we have this algorithm, division algorithm. So we start with an example, and then now we go to this algorithm. So if we wanted to divide f of x, or if we have, for example, two polynomials, f of x and d of x, and if d of x is different from 0, then, and if the degree of this d of x is less or equal to the degree of this f of x, then we can divide this f by d, okay? And if we can divide it by d, then we can write f of x as d of x times q of x plus r of x, okay? We can write it this way. And this d of x is the divisor, q of x is the quotient, and r of x is the remainder, okay? We have all this. So this is what we call the division algorithm. And you can even use this real numbers that we did earlier to write this one. So for this one, I can write 244.67 is the same with 3 times 3 is, in our case, this is d of x. This is f of x. And 8,489. This is q of x plus, in our case here, the remainder is 0. So let's just put it here, and this is r of x. Okay. So using real numbers, we can still write the same way. So this is what we are calling the division algorithm. And the next one is the synthetic division. So this synthetic division is a kind of special one, and we use it only when the divisor is in the form of x minus c. I cannot use it any time. For example, if we have x squared minus 4, then we cannot use the synthetic. If we have x cubed plus 4x plus 5 as a divisor, then we cannot use the synthetic division. Okay, we only use the synthetic division if we have degree 1. It has to be degree 1. Okay. Okay. So let's say we have a divisor which is degree 1, which can be written in the form of this one. And it's not only degree 1, but the coefficient has to be 1 as well. Yeah, that one again, it's important. The coefficient of x has to be 1. Now, suppose we have this form, x minus c, as a divisor. And a simple example is this one. So if we have x plus 2, we wanted to divide this number by x plus 2. But we have to write x plus 2 as in the form of x minus c. Okay, we need it to be this way. And to do so, I can write this one as x minus minus 2. Therefore, if I write this one in a more proper way, I put parentheses here. So I can write this one, and this looks like this, right? So my c is now negative 2. Okay, so when it's plus, you take the negative side. When it's minus, then c is that number itself. If we have, for example, x minus 3, if this is x minus 3, then our c is 3. If we have x plus 2, our c is a negative 2. It's the opposite. So in this case, our c is minus 2 or negative 2. Now, we wanted to divide this polynomial by x minus 2, and obviously, or we of course, the divisor is in the form of x minus c. Now, what we do is take c, and write the coefficients of from the highest to the lowest, the coefficients of this polynomial. So this, in our case, RC is -2. And the coefficients starting with the highest degree is 4, -12, -27, 30, and 8. And here you leave some room between this coefficient and between this line, because we are going to write something in here. And then you bring this 4 down here. Okay, the first term, you bring it without any operation, you bring it down here. And then what we do is we multiply this number and this number. We use multiplication. This is multiplication. Okay, so -2 times 4, we write it here -8. Okay, and then we add these two numbers, this one and this one, we add them, and that's -20. Okay, we add these two numbers. And then we follow the same idea. 4 times sorry, not 4. Again, this one. Let me use a different. Okay. And the next is -2 times this one, and that's +40. And again, add this two numbers. I'm going to write it here just to show you that we are adding. We're not subtracting now. So if you add these two numbers, we get -27 plus 40, which is +30. And then we do the same thing. We follow -2 times 13 is -26. And again, we add them. 30 plus -26 is +4. And then we multiply this, -2 times 4. This is multiplication, okay? This is -8. Again, we add them. This is 0, okay? So this is the remainder. Here, this is the remainder. And these are the coefficients of the quotient, okay? These numbers are the coefficient of the quotient. Now, the thing is, how do we determine what the quotient look like, or the degree of the quotient? Well, since we are dividing this one, this is degree 4, this polynomial is degree 4, and the divisor is degree 1. Therefore, the quotient has degree 1 degree less than this one. So if this is degree 4, the quotient will be degree 3, because when you divide x to the 4th by x, which means this one, the result is x cubed. Okay, so the quotient will have, it will be a cubic function. Therefore, this is corresponding, this coefficient is corresponding to x4, this was corresponding to x cubed, and this x squared, x, and this was constant, right? And similarly, this is corresponding to x cubed, this is to x squared, this is to x, and this is constant. Therefore, my function, my quotient is 4x cubed minus 20x squared plus 13x plus 4. Okay, so this is the quotient. And of course, the remainder is 0. Okay, so this is, it's easier, much easier. The synthetic division is much easier as long as our divisor is in the form of this x minus c. We can always use the synthetic division because it's much easier, simpler, and shorter. So here I put this two long division and synthetic division. So as you can see, even the steps, this is long and this one is short. but we end up with the same result. Okay. All right, and the next is the remainder theorem. And the remainder theorem says if a polynomial f of x is divided by x minus c, then the remainder is f of c. And this comes from the division algorithm. The division algorithm says f of x is d of x times q of x plus r of x, right? So if f of x is divided by x minus c, so if this divisor is x minus c, then f of x equals to x minus c times q of x plus r of x. We have this, right? And this r of x, it's always a constant in this case because we are dividing the polynomial by x minus c by degree 1. So the remainder is always, the remainder has to have a degree less than this one, okay? Less than the divisor. So a degree less than this one, because this is degree 1, this has to be constant. Therefore, I will just write it r, okay? So here, what this is saying is if we divide this one, then the remainder is f of c, okay? Now, we have this one. So what is f of c? This is our remainder, right? So f of c has to be r in order this to be true. So let's evaluate this one at x equals to c. F of c, if I replace this by c, we get c minus c times q of c plus r. C minus c is 0, 0 times q of c is 0, so this is just r. So f of c is r, and r is the remainder, f of c is the function evaluated at x equals to c. Therefore, we have this theorem, okay? The remainder is f of c. For example, now let's look at this one. So if we have a function, h of x equals to 5x cubed, then use the remainder theorem to evaluate h for the given values of x. So we wanted to find h of 1 equals to -2. Now this is the remainder, right? This is r. And c is, in this case, c is 1. Let me see. C is 1. Therefore, we need to divide this polynomial by x minus c, which is x minus 1, and then we get the remainder -2. Okay, we are just trying to evaluate if this is true or not. Therefore, I will use the synthetic. I will put c here, and the coefficients are 5, -4, -15, and 12. So I will bring 5 down here. 1 times 5 is 5. If we add them, we get 1. 1 times 1 is 1. If we add them, we get -14. This is -14. We have -2. This is the remainder. And as you can see, this is the number itself. Okay? Therefore, this is true. How about this one? Or maybe I will skip this and come to this one. And h of √3 equals to 0. So if we divide, here our c is √3. If we divide the polynomial by x minus 3 by x minus √3, the remainder has to be 0. Therefore, using the synthetic division, let's again write the coefficients. And this is our c. We have 5. 5 times this one is 5√3. And then if we add this, we get 5√3 minus 4. And then if we multiply this, what do we get? It will be 15 minus 4 root 3. And then if we add this, we get negative 4 root 3. Then this one times this, it will be negative 12. And again 0. Okay. And as you can see, this is again true. So similarly, we can check the remaining. Okay. We can check the remaining. So maybe I can do the last one. Negative 1. So in that case, our C is negative 1. So it will be negative 1, 5, negative 4, negative 15, and 12. 5, negative 1 times 5, it will be negative 5. And if we add this, we get negative 9. And this is positive 9. And we have what do we have? Oh, negative 6. Right? Oh yeah, negative 6, and then negative, this is negative 1 times this one is positive 6, and then we have 18. Okay, so this, the remainder in this case is 18. And again, of course, you can evaluate it. Negative 1 here is negative 5, negative minus 4, plus 15, plus 12. This is 9, this is 27. 27 minus 9 is 18, of course, so we get the same result. Okay, we can just evaluate it at x equals to negative 1 and we get the same result. And using the remainder term, we get the same result. Okay. All right, I think I will stop right here and we will continue this one in the next lecture because I think the video is becoming too long. So yeah, let's stop. Let me stop here. All right, so see you in the next lecture.